Let's consider section 3.4. We'll study finding the zeros of a polynomial function and the fundamental theorem of algebra. In this section, we're going to use a number of tools. One of our first tools is going to be the rational zero theorem. This theorem tells us if I have a polynomial with integer coefficients and p over q is a rational zero of the polynomial that's in reduced terms or lowest terms, then p has to be a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. Very powerful, very useful theorem. Next, we're going to be using the properties of roots of polynomial equations. So the first property we're going to make use of is the fact that if a polynomial equation has degree n, then counting multiple roots separately, the equation has n roots. The second property we're going to use is that imaginary roots, a plus bi, where b isn't 0, come in conjugate pairs. So if a plus bi is a root of the polynomial equation, and notice the coefficients are real numbers, then so is the imaginary number a minus bi. And then we're going to also use the fundamental theorem of algebra. And that tells me if a polynomial of degree n, where n is bigger than or equal to 1, is set equal to 0, that equation has at least one complex root. And remember, real numbers are considered complex numbers. Another tool for this section that we'll need is the linear factorization theorem. That theorem tells me if I have a polynomial that's degree 1 or bigger and the leading coefficient isn't 0, then the polynomial can be written in the factored form that's shown. Notice the constant monomial factor here is a sub n, the leading coefficient of the polynomial. And then that will be multiplied by, so in this factored form, the leading coefficient will be multiplied by n linear factors. And notice each linear factor has a leading coefficient of 1. And c sub 1, c sub 2, all the way up to c sub n are complex numbers. Some of them may be real, some of them are not necessarily unique. And that's the thing to keep in mind. Very, very powerful theorem that we'll make use of. And then in this section, you'll also need Descartes' rule of signs. So that tells me if I have a polynomial with real coefficients, the number of positive real zeros of the polynomial is either the same as the number of sign changes of the function or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f has exactly one positive real number. The number of negative real zeros of f is either the same as the number of sign changes in f of negative x or less than the number of sign changes in f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. Please view the video that I've made on and have posted in D2L on number 35 from section 3.4 that goes over the use of this rule. We won't cover that in this video. On our first problem, we want to find the remaining two zeros of a 6-degree polynomial whose coefficients are real numbers and has the zeros 2, -3, 2i, and 1 minus 2i. So that's our task here. So the first thing we want to do is we want to remember the fact that every nth degree polynomial has n zeros. So this is a 6-degree polynomial, and we only have 4 of the zeros. So there are 2 more zeros. So that's the first property of a polynomial and its zeros, is that a 6-degree polynomial has 6 roots. So that's one of the properties we want to make use of first. We know that we need to find, therefore, 2 more roots. So imaginary roots come in conjugate pairs. So that's another property of roots of polynomials that we need. So that basically means if 2i is a root, so is -2i. And if 1 minus 2i is a root, so is 1 plus 2i. So that's what the second property of roots of polynomial equations tells us. So in other words, the remaining 2 zeros are -2i and 1 plus 2i. So that's really all I'm being asked to do in this first problem, is find the remaining zeros. All right, in number 2, I want to find a polynomial of degree 5 whose coefficients are real that has the zeros 0, -2i, and 2 plus I. So using that conjugate pairs property of the zeros of a polynomial, we know that this polynomial has 5 zeros, and if -2i is a root, so it's 2i, and if 2 plus i is a root, so it's 2 minus i. So now we're going to use the linear factorization theorem. And we know the polynomial, this 5th degree polynomial, can be written as a5 times x minus 0 times x minus -2i times x minus 2i times x minus 2 plus I times x minus 2 minus I. So that's how I would write this 5th degree polynomial in factored form. We're going to make our life easy. A5 can actually be any non-zero real number. So we're going to make the easiest choice, since we were just asked to find a polynomial that has these zeros. We're going to let A5 equal 1. And then we're going to simplify this factored form by replacing A5 with 1, which we can leave unwritten, and writing x minus 0 as x minus -2i is x plus 2i, x minus 2 plus I is x minus 2 minus I, and x minus 2 minus I is x minus 2 plus I. So we're just distributing the negative signs as appropriate. And I'm going to use the fact that whenever I have some first term A plus a second term B times a minus b. That's always a squared minus b squared. So I'm going to multiply x plus 2i times x minus 2i, and that gives me, so my a is x and my b is 2i. That gives me the square of x minus the square of 2i, which is x squared minus 4i squared. And remember, I is negative 1. So this is x squared plus 4. Now I'm also going to multiply x minus 2 minus I times x minus 2 plus I. This is also a difference of squares. So notice here, this is an a minus b times an a plus b, where my a is x minus 2 and my b is simply I. So this is an a minus b times an a plus b. Now notice I need to square x minus 2. Well, that's actually the square of an a minus b, which if I use FOIL, which is the double use of the distributive property, then I get a squared minus 2ab plus b squared. So in this, when I square out x minus 2, my a is x and my b is 2. So this is the square of x minus 2ab, 2 times x times 2, plus b squared, which is 2 squared. And then I remember that the square of I is negative 1, the imaginary unit I. So this becomes x squared minus 4x plus 4 minus a negative 1, which is the same as plus 1. So this is x squared minus 4x plus 5. All right, so when I go to put this information back into the product that's going to give me my polynomial, so notice I'm going to replace x plus 2i times x minus 2i with my result that I've got initially. And then secondly, I got the product of x minus 2 minus I times x minus 2 plus I. So f of x is x times, so that first product, x plus 2i times x minus 2i, remember that was x squared plus 4. And then the second product, x minus 2 minus I times x minus 2 plus I, remember that came out to be x squared minus 4x plus 5. So now I've simplified this somewhat. So I'm now going to multiply the last two expressions together. So I'm going to multiply x squared plus 4 times x squared minus 4x plus 5. And I'm going to use the distributive property twice here in order to do this. So the x squared gets multiplied by x squared minus 4x plus 5, and so does the positive 4. And so I just distribute, and I get x to the 4th minus 4x cubed plus 5x squared plus 4x squared minus 16x plus 20. And then when I combine the 5x squared and the 4x squared, that x squared term is actually 9x squared. So x to the 4th minus 4x cubed plus 9x squared minus 16x plus 20 needs to be multiplied by x. So when I do that distribution, I get x to the 5th minus 4x to the 4th plus 9x cubed minus 16x squared plus 20x. So this is a 5th degree polynomial with the zeros that I needed. that were indicated. All right, the third problem, I want to find the complex zeros of the polynomial function 2x to the fifth minus 6x to the fourth plus 6x cubed minus 18x squared minus 8x plus 24. Now we know that the rational zero theorem, from that theorem, that if there are rational roots, they have to have the form p over q. P has to be a factor of a sub 0, our constant, which is 24. So I've written all the possible integer factors of 24. And then q has to be a factor of a5, which is since this is a fifth degree polynomial, that's my leading coefficient, which in this case is 2. So q is a plus or minus 1 or plus or minus 2. So now I take every integer in the numerator and individually put it over every integer in the denominator. So when I put 1 plus or minus 1 over plus or minus 1, I get plus or minus 1. When I put plus or minus 1 over plus or minus 2, I get plus or minus 1 half. Plus or minus 2 over plus or minus 1 is plus or minus 2. Plus or minus 2 over plus or minus 2 is plus or minus 1, and that's already written. And I just keep doing that until I get the list that you see. So let's start. My recommendation on these problems is to always start with simple small integer values or use a graphing utility. And the graphing utility will help you to see the x-intercepts and which of these in the list could possibly be just by looking at the graph. So I'm going to start by using synthetic division and checking to see if x equal -1 is a rational root. So I write the coefficients of the polynomial and I do the process of synthetic division. And notice I do get a remainder of 0. So that means x equal to 1, -1, is a 0 of this polynomial. Now let's see if it's a 0 with a multiplicity greater than 1. So now we take the quotient coefficients, 2, -8, 14, -32, and 24, from the previous synthetic division. And when we see we don't get, and we do synthetic division again. So we see we don't get a 0 remainder, then that means the multiplicity of -1 is simply 1. All right, now let's try 1. Let's see if that's a 0. Bring down the 2, multiply by 1, add that to -8, and repeat the process. And I see that I do get a 0 remainder. So that means 1 is a 0 of the polynomial. Let's see if 1 has a multiplicity greater than 1. So we use the coefficients of the quotient from the previous synthetic division. And we repeat the synthetic division process. We do not get a 0 remainder, so 1 only has a multiplicity of 1. Now let's try 2. See if 2 is a 0. We don't get a 0 remainder, so 2 is not a 0 of our polynomial. Let's try -2. So we go through the process. Bring down the 2. And notice we're writing the coefficients of the last time we got a remainder of 0. And notice -2 is not a 0. We are not going to get a remainder of 0 there. I didn't even finish it because I know that's not going to be 0. And notice when I try 3, I do get a remainder of 0 when I go through the synthetic division process, so 3 is a 0. So the zeros so far are -1, 1, and 3. The quotient from our last successful synthetic division, and when I say successful, I mean we got a remainder of 0. Notice we got the coefficients 2, 0, and 8. So the quotient then is actually 2x squared plus 0x plus 8, which is 2x squared plus 8. So we can now factor the original polynomial into f of x equals x minus negative 1 times x minus 1 times x minus 3 times this quotient 2x squared plus 8. And I didn't mean to have that 2 there yet. We are going to get a 2 there, but not yet. All right, so that's our original polynomial in a semi-factored form. We notice we can factor a 2 out of 2x squared plus 8. And let's put that in the front. And when we factor 2 out of 2x squared plus 8, that becomes x squared plus 4. So we're going to find the remaining two zeros by solving x squared plus 4 equal to 0, and we're going to use the square root property to do that. So x squared plus 4 equals 0. If I subtract 4 from both sides, I get x squared equals negative 4. The square root property tells me I can lose that exponent of 2 on the x if I apply plus or minus square root to the negative 4 on the right. And that simplifies to plus or minus 2i. Since the square root of negative 4 can be written as square root of 4 times square root of negative 1, and the square root of negative 1 is I. So the complex zeros of the given polynomial are negative 1, 1, 3, and 2i, and negative 2i. All right, number 4, we want to solve 16x to the 4th minus 1 equals 0 in the complex numbers. So we can use factoring to solve this. So this is actually a difference of squares. 4x squared squares to give 16x to the 4th, and 1 squares to give 1. So we're using the fact that this is a difference of squares. And notice, if we think of this as a squared minus b squared, our a is 4x squared and our b is 1. So this factors into a plus b times a minus b, which for our situation is 4x squared plus 1 times 4x squared minus 1. So remember that a sum of squares is prime. But 4x squared minus 1 is the same factored form, special form, a difference of squares. So we can factor this again, where now our a is 2x and our b is 1 again. So 4x squared minus 1 factors into 2x minus 1 times 2x plus 1. So the zero product principle tells me if a times b times c equals 0, then a equals 0 or b equals 0 or c equals 0. So I'm going to find the solutions. My a in this case is 4x squared plus 1. I set that equal to 0. I use the square root property, and I wind up getting x is plus or minus square root of negative 1/4, which is plus or minus 1/2 I. B, in this case, is 2x minus 1. When I set that equal to 0, I get x equals 1/2. My C is 2x plus 1. When I set that equal to 0 and solve, I get x equals 2, negative 1/2. So the zeros of the polynomial are negative 1/2 I, 1/2 I, 1/2, and negative 1/2. And these are the solutions to the equation. So I want to form a fifth-degree polynomial with real coefficients whose zeros are 3i, 1 minus 5i, and negative 1, and f of 0 is negative 3. So we know that if 3i is a 0, so is negative 3i, and if 1 minus 5i is a 0, so is 1 plus 5i. So we're using that conjugate pairs property of polynomials. the zeros of a polynomial. So let's factor this. We're going to write this polynomial as a5 times x minus the 0, -1, times x minus the 0, -3i, times x minus 3i, times x minus the 0, 1 minus 5i, times x minus the 0, 1 plus 5i. And notice we actually have to find what a5 is. We can't choose our a5 this time because we are asked to find the one and only one fifth-degree polynomial that has the 3 given zeros, and that if x is replaced with 0, the polynomial becomes -3. All right, so we simplified this so that we don't have any double parenthesis or parenthesis inside a parenthesis. And we're going to do the product x plus 3i times x minus 3i first to get x squared plus 9. And then we're going to do the product x minus 1 plus 5i times x minus 1 minus 5i. And we're going to look at this as an a plus b times an a minus b, where a is x minus 1 and b is 5i. And when we square x minus 1, we get x squared minus 2x plus 1. And when we square 5i, we get minus 25i squared, which simplifies into plus 25. So this becomes x squared minus 2x plus 26. So f of x is whatever our a5 is going to be, times x plus 1, times x squared plus 9, times x squared minus 2x plus 26. So this is real similar to what we were doing on problem 2, but it's actually a little more complicated because we can't choose our a5, we have to pick it. All right, so notice I used the distributive property twice. X squared plus 9 gets multiplied by x squared minus 2x plus 26. And notice how I applied the distributive property twice. I multiplied the x squared times the trinomial and then the plus 9 times the trinomial. And I combine like terms, carry out that double use of the distributive property, combining like terms. I get x to the fourth minus 2x cubed plus 35x squared minus 18x plus 234. And that gets multiplied by x plus 1 and times our a sub 5. And now I'm going to use the distributive property twice again. The x gets multiplied by the x to the fourth minus 2x cubed plus 35x squared minus 18x plus 235, and so does the plus 1. That also gets multiplied by x to the fourth minus 2x cubed plus 35x squared minus 18x plus 234. And there should have been a bracket on the end of that. So when I multiplied that x by that polynomial, I get what you see written. And when I multiply by 1, I just get that polynomial again. And now I need to combine my like terms. And notice negative 2x to the fourth plus x to the fourth is negative x to the fourth. Plus 35x cubed minus 2x cubed is plus 33x cubed. Minus 18x squared plus 35x squared is plus 17x squared. Plus 234x minus 18x is plus 216x, and then I recopy the plus 234. So now I'm going to replace all of my x's with 0, and when I do, this polynomial has to equal -3. So notice this is going to allow me to find a sub 5, the leading coefficient of the polynomial. So I replace all the x's with 0. And notice all the terms become 0 since multiplication by 0 is 0. And I wind up with negative 3 equals a sub 5 times 234. When I solve for a sub 5, I divide both sides by 234. I get a sub 5 is negative 3 over 234. And that actually simplifies to negative 1. 234 is 3 times 78. I can divide out these common factors of 3. There's a factor of 3 in the numerator and denominator. Those divide out to give 1. So I get negative 1 over 78. That is what a sub 5 has to equal. So f of x is negative 1 over 78 times x to the 5th minus x to the 4th plus 33x cubed plus 17x squared plus 216x plus 234. And I can distribute that. I'm not sure if the My Math Lab requires you to distribute that or not. So just in case on a problem like this it does, I'm going to go ahead and distribute this. So I multiply each term of the polynomial by negative 1 over 78. So I get negative 1 over 78 x to the 5th plus 1 over 78 x to the 4th minus (33 over 78 x cubed) plus 17 over, and actually this is a minus since I'm multiplying by a negative 1 over 78. So I get minus 17 over 78 x squared minus so this is a minus. I meant to write minus here. To 16 over 78 x minus 234 over 78. Okay, and I'm going to simplify any coefficient that can be simplified. So the first two terms are going to remain as is, but 33 and 78 can both be divided by 3. So when I divide 33 by 3, I get 11. When I divide 78 by 3, I get 26. So I'm going to be able to reduce that. 216 and 78 can both be, they also have a common factor. And both of those can be divided by 6. So 6 goes into 216 36 times. 6 goes into 78 13 times. And then 78 actually divides evenly into 234. So 78 goes into 78 once. 78 goes into 234 3 times. So this allows me to simplify f of x into the polynomial negative 1 over 78 x to the fifth plus 1 over 78 x to the fourth minus 11 over 26 x cubed minus 17 over 78 x squared minus 36 over 13x minus 3. And that is our final result. So that's the only fifth degree polynomial that satisfies the conditions. F of 0 is negative 3, and this polynomial has the 5 zeros that we needed to have.